Hello, my name is Daniel Medine. I'm the team lead for the Flare Director project. This is Logan Skirville, and Devin. So as an overview for today, we're going to go over the purpose and motivation behind this project, the design that we've chosen over the last semester and a half, our test results and analysis of those test results, as well as any future work and opportunities we think that could enhance this product down the line. And then we'll also have a question sessions at the very end. So if you think of questions, please leave them for the end. So first, the purpose and motivation. So what is the Flare Director and how can it help? So first off, the flare. The flare is a move in the final maneuver when you're landing an aircraft before touchdown. And the pilot must be aware of their altitude, and what they do is they pull back on the yoke, increasing their pitch so they level out when they hit the runway. It's a safety critical moment during flight, and a lot of student pilots struggle with this maneuver, often hitting their gear or doing other damage to the aircraft. In addition, rusty pilots who haven't flown in years struggle with this maneuver too. And bad maneuver can be very costly. So another thing is it's very difficult to judge your altitude above ground level. You typically only have visual cues, and there's often a lot of optical illusions and problems as you're approaching the runway, where you may gauge a distance incorrectly, depending on slope or width. And finally, of course, at night, your visibility is not nearly as good. You lack focal points and ground points, and therefore it's a lot harder to land at night than it is during the day. So I now want to show you a video of someone not flaring their aircraft. So that's what we want to try and avoid, and that's what this product is trying to avoid. So now, in addition to all of that, there's actually a market for this kind of problem. So obviously, as I've already mentioned, student pilots would be very enticed to this, as well as rusty pilots, those who haven't flown in a while. And for the student pilots, obviously flight schools would be very interested in a product like this because they could attach it to their aircraft and ensure the quality of their training and decrease their hours and cost during flights. And there's currently no alternative out there for a general aviation aircraft at a low cost for an altimeter like this. Everything is extremely expensive and usually built for larger commercial grade aircraft. And as well, new technologies are being available at the moment which allow a product like this to be a lot more affordable. And so the concept of the Flare Director is that we're going to have a system of wireless modules. So we're going to have two modules in particular, the altitude sensing module called the ASM, and the altitude reporting module, the AR. The altitude sensing module measures the altitude above ground level, and then reports that information to the altitude reporting module wirelessly into the cockpit, and then the pilot hears that reporting via a non-visual mean, aka audio. So they hear in their headphones 80 feet, 50 feet, 40 feet, and so on. With that, we're now going to highlight some requirements. So the first is that I bolded and underlined the key requirements. We want this to be able to measure the altitude above ground level between 0 and 80 feet, which is the last few seconds of landing. In addition, it must wirelessly connect from the ASM to the arm and vice versa. We don't want to run wires through the plane or connect it to the plane. That gets too complicated. In addition, FAA certification is not required during this portion of our design. And one other thing I wanted to note was we are going to get within plus or minus 5% accuracy, and obviously as you get lower to ground, that tightens. So with that, we'll now move into the system design.
Thanks, Dan. So let's hop right into some of the system design that we have for this project. The first of which, this is a high-level block diagram for a project. We had our sensors that we chose that I'll get into in a bit, and then those were connected with the ASM, the altitude sensing module, which would then distribute the data to any of the arms that were connected to it, the altitude reporting modules, which would then give those altitudes to the data, to the pilot or the instructor, whoever had their headsets on. So let's go into the first module. We'll talk about the altitude sensing module. The first thing to note is with the altitude sensing module is that we actually had to have physical sensors on there to be able to sense any of the data for the altitude. The first one that we chose was the LiDAR. This sensor, we chose a Garmin LiDAR Light V3HP, and LiDAR works by measuring the distance using light reflection. And so pros to this type of sensor is that it actually has a long range. This sensor alone can work up to 40 meters, which well exceeds our requirements of 80 feet. And in addition, it has high accuracy. However, for cons, with LiDAR, it actually has to have the optical sensors need to not be obstructed. They need to be able to receive and send light. And then it also maybe possibly unreliable with reflective surfaces. However, in some of our tests, that proved to be actually reliable. The next sensor that we chose to use was the sonar, and this was an ultrasonic from Max Sonar, and this measures data using ultrasonic pulses. The pros for this is that it's actually it's highly precise at low ranges, and it uses low power. However, it is a very short range sensor, and so this one we have is about 10 meters. And so we wanted to use this to be a redundant sensor as we get closer to the runway to make sure that both the sensors are getting accurate data. However, as we're going to show later on in some of our test slides, this sensor proved to be relatively not valuable for this project. However, we did have to do some sensor fusion and weighting for these to be able to make sure that we were getting good, accurate data. And we used these schemes to be able to work with it. We said LiDAR, we're going to trust 90%, while with sonar, we're going to trust 10%. And this is another one that's going to come up when we come to the tests and the test analysis that Devin's going to talk about later on. Formula, we simply used an averaging with the LiDAR at 90%, sonar at 10%. And then for future software versions, depending on if we use other sensors or not, we can have different weighting for different thresholds after more tests that we decide to conduct. Now, hopping into the software and how this works, this is a quick software flowchart. So we start with the ASM, power it on, and it checks the sensor configuration, saying, all right, is everything connected? If it's not, we're going to alert the pilot through the interface and say, hey, the hardware is failing. Don't actually don't look at this. And then otherwise we're going to wait for this. We're going to say, is the calibration good? Nice. All right, we're good. So then we're going to go into a sleep mode that we're going to slowly acquire data at a slower acquisition rate until the pilot actually turns the reporting mode on. Once the reporting mode's on, which would be when they're landing, it's going to send the sensor data acquisition. It's going to say, it's going to process this, and then it's going to encode these TCP packets that's going to get sent to the application, the altitude reporting module, which is going to be inside the cockpit. And then it's going to continually do that as the reporting modes continue to turn on. And that is how the software is designed. But how's the electronics for this design? And this is some of the details that we had to go through for this. We wanted to make sure that for the electronics, we had interconnectability between the sensors, that we could get data from both the sensors, that all of this would be working properly. We wanted to just use a simple off-the-shelf microprocessor module. We didn't want to have to work with creating our own microprocessor board to be able to do any of this acquisition. We also, for the battery power, we wanted to just have a simple battery power pack with charging and monitoring to where we'd be able to report the battery percentage to the pilot inside the cockpit and have it be rechargeable so they wouldn't have to, switch out batteries all the time. And this would be more of a user interface issue with that, which would be pretty nice. We also wanted to have modularity to enable testing and additional sensors, so we could expand this in the future, and we'd be able to say, all right, if we wanted to add another sensor here, we have other spots available for it on this, so then it would actually already be modular, and we wouldn't have to redesign anything. And then in addition, we just wanted to make it robust enough for flight testing. We wanted to make sure that if this actually went up in the air, when it goes up in the air, that this isn't just going to disconnect and it's not actually going to be robust enough to actually function as the product that we really want it to function as. And for that, this is the board layout and board design we ended up coming out with. So for the microprocessor unit, we actually use a Raspberry Pi. And for the board layout, we just connect all the GPIO pins. We have interconnections, we have LED 7-second display for error correcting codes that we can see visually so we can get those reports as well. And in addition, we use the PC board as essentially a mounting method for both the sensors. So this way we could have the sonar mounted on this and the LiDAR mounted on that to give it just more of a backbone so it would be more robust for those flight tests. And all populated, this is what the final PCB looks like. As you can see, we have the sonar over here mounted, we have the LiDAR over here mounted, we have everything soldered on, and the PCB has been working fantastic, and as a mounting method, it works great as well. Now for the power budget, this is powered all by a power supply for a Raspberry Pi. We use two 6,000 milliamp hour batteries in parallel, accumulating to 12,000 milliamp hour battery. And with the current draw, let's say we have it in use for the full recharge of all the batteries, the expected hours of use we expect is about 14 hours. And that has been relatively stable for all the tests that we've been doing. We've been getting good power out of it. We've we've been getting good battery life, and it's worked and functioned well for the tests that we've had. Now, to give it to Devin to talk about the housing.
So some of the concerns that we had when building the housing was that we had to make sure that the attachment method was not going to damage the skin of the aircraft. So as such, we used suction cups to ensure that it wouldn't tear off any of the aluminum or damage it anywhere like that, as well as it could not hinder any of the aircraft performance, so it still had to be able to maintain that good aerodynamic profile. It had to be able to endure up to 150 knot winds and contain all necessary hardware for the ASM. And it had to be relatively weather tight, though that wasn't a huge concern with our project since this was purely a prototype. And so the first thing we did was design a CAD model of this with help from some of our AE friends. And so you can see here that the top module is the Raspberry Pi, and that is mounted to the top plate of the acrylic. The middle is the power, and then the bottom is that PCB right there with the LiDAR and the sonar sticking out of pre-drilled holes in the acrylic. So this is our first build. The first thing we did was we got some heavy-duty acrylic material, which we then bonded with epoxy. We also had some L brackets here for extra stability, and then we chose the suction cups that we have based upon their strength under stress. And this is purely intended to contain the electronics, and it provides minimal environmental protection. So in a future version, we would want to add some more environmental protection for this. And so now Grant is going to talk about the ASM to ARM communication.
So one of the big requirements for the modules was they had to wirelessly communicate because we didn't want to run wires from inside the cockpit to the other side of the aircraft. So the way the wireless communication works is the Raspberry Pi actually configures itself into a Wi-Fi access point or a hotspot, and then the tablet connects to that Wi-Fi hotspot, and we send data through Wi-Fi. More specifically, the Wi-Fi is the 802.11b standard, which gives us 11 megabits per second, which is plenty for our needs. And our preliminary testing of the Wi-Fi range has produced favorable results. And another reason we chose Wi-Fi is for the signal strength, because the aircraft, since it's made out of aluminum, it acts like a Faraday cage. So electronic signals, it makes it harder for the electronic signals to penetrate the aircraft. So Wi-Fi has a stronger signal propagation than something like Bluetooth low energy. So the system data flow diagram, so this kind of illustrates, how the sensor data gets from the sensors all the way to the application onto the altitude reporting module. So we take the data from the LiDAR and the sonar, and the data from the LiDAR comes through the I2C data bus, and the data from the sonar comes through the serial data bus. And we have software classes, the LiDAR interface class and the sonar interface class, that handle the sensor data acquisition for both sensors. And we feed that data into an altitude provider software class, which performs the signal processing and averaging of the sensor data. We then provide that averaged data to the socket transmission thread, which then sends that data over Wi-Fi through TCP packets to the altitude reporting module inside the cockpit, which then retrieves that TCP packet, decodes it within the application logic, and decides how to play that back through audio. And then the pilot or instructor hears that audio through their headset. So now we're going to talk about the altitude reporting module. So that's the tablet located inside the cockpit. So here's the high-level block diagram of how this works. So like we said before, the altitude data is sent over Wi-Fi to the altitude reporting module, which is the tablet or smartphone. And then it is, the audio is played to the pilot instructor's headset. So there's a couple different ways we can get the audio to the pilot instructor's headset. A lot of newer aircraft have an audio auxiliary input, so we would just run a simple 3.5 millimeter cord from the tablet into the panel. Or you could use a series of extension cables and splitters to directly connect the tablet to a single headset. So the altitude reporting model software flowchart, so this is kind of what's going on inside the software. So when you start up the application attempts to connect to the altitude sensing module. If it can't connect at first, it continually tries to connect until it can. But when it does connect, it requests a system status from the altitude sensing module, so we get the sensor status and the calibration status and stuff like that, so that we can display that on screen and alert the pilot if there's any type of hardware failure. But once everything is okay, we start listening for TCP packets, and when the altitude sensing module is in reporting mode and it's actually sending data to the tablet, we decode the packet, handle any type of events or operations, decide if we should play an audio alert, and play the audio enunciation to the pilot. So this is what the user interface for the altitude reporting module looks like. It demonstrates data from each measuring device. So we have a LiDAR section here and a sonar section here. And we also, at the top, have the processed altitude in a big font. And then we also show the system status. We show if it's disconnected or connected. And then we also have the battery level. And then we also report if the sensor is failing through an on-screen and audio alert. So if for some reason the pilot's flying and he's about to land, and for some reason the sensor becomes unreliable or fails, he'll actually hear an audio alert that says sensor failure. We can demonstrate that a little later. So going more into the human interface, this is kind of where the pilot interacts with the whole system. So up at the top here, we actually have two options for the pilot to receive altitude enunciations. They have a synthesized voice option and then a beeps option. So for the synthesized voice option, it literally just tells you 50, 40, 30, 20, 10 as you're landing. But with the beeps option, the beeps increase in frequency as you get closer to the ground. So this button right here, that's the turn on reporting feature. So right now, as the system is designed, the pilot has to manually turn on reporting for the sensors to start pulling at high frequency and for the altitude data to get sent to the tablet. And we also have our battery level here, and then we also have a button to calibrate the sensors because you want to be able to have that accurate result if the ASM is mounted to a high-wing aircraft. And then we also have a button that allows us to turn on data logging. So one of the features/requirements we had were basically a landing profile playback. So we're able to log that data and then take that data, offload it, and then graph it and see a visualization of your landing. So now we're just going to play a quick video that kind of illustrates how this works.
80, 50, 40, 30, 20, 10, 5.
Nice landing.
So now,
You want to do it?
oh yeah, we can do a quick demo.
Yep. So I can actually, do you want to pass this around?
Sure thing.
We can just like turn recording on and pass it
Yeah, we got to calibrate first.
Yep.
Yep. So what we're going to do now, so picture this, the ASM's turned on, it's mounted to the aircraft, and the pilot gets in, he's strapped in, and he pulls out his tablet, fires up the application, it's connected. So right now, what I'm going to press calibrate, the sensor goes through the calibration process, and it's calibrated. And then let's say the pilot's in the air, he's about to land, he presses the reporting button.
You want to show around?
Yeah.
So that now, yes, 10.
You can see on the display, we're getting real-time readout of what the sensors are seeing. And then you can hear the little voice saying what the else is.
20, 10.
And then just real quick, just to demonstrate the error detection. So I'm actually gonna unplug one of the wires on the sensors.
Where direct your sensor failure.
So it shows that the sonar has failed, it reads it out to the tablet, and the pilot is well aware of it. The same is true with the LiDAR, if we unplug it, if we somehow disconnect it.
So now getting into some testing results that we had. The first thing that we did was we tested each of the sensors to ensure that they fell within the 5% accuracy range. And so to do that, we went down to the gym and just measured at a known distance and pointed out a wall and tested that way. We found that the LiDAR falls within its 5% requirement from ranges of 5 centimeters up to 38.8 meters. And the sonar falls within the 5% range at 3.6 meters. And the reason for that is that it's highly dependent upon field of view. The sonar sends out a very large cone, and as such, if you point out a wall, it's going to also detect the ground. And so some of the time it would also send back the ground distance as well. And so that's one of the reasons why we decided to have such a high trust in the LiDAR and our weighting algorithm. And so here you can see our 3.6 meter test. You can see that the LiDAR is in blue and the sonar is in orange. This is true for all of these graphs. You can see that the LiDAR fell within 3% range for all of its values, and the sonar read within 1% of its range every single time except for these couple of outliers, which we believe is because of the field of view inherent with the sonar. Now at 10 meter test, which is the full range of the sonar, you can see that the LiDAR was still very accurate, falling within 1%. And the sonar, when it actually read the distance it was supposed to, it read it very well. But it would also detect here, about 6 meters, quite often, which is presumably from the field of view that it has. And so you can see that that is going to be, it would be a very large problem with this thing. One of the things that we were thinking was when it's in an aircraft, it's not going to have the ground to hit, it's only going to have that to hit. But we couldn't really simulate that kind of testing on the ground outside of an aircraft. And so at 30 meter test, which is well out of range for the sonar, you can see that the LiDAR hit its mark within 1% tolerance every single time. And so for our next testing procedure, trying to make it so the sonar would not read the ground, we decided to try to rappel over at the Dells. And there was a little overhang right here that we were going to try to go to, so hopefully the sonar wouldn't actually detect the rock. However, when we were doing this, there was a problem with our power source, that it would power cycle often, and that caused our data to be corrupted. However, looking at the data like on the actual app, it looked like the LiDAR was still very accurate, but the sonar was still detecting the wall even on this test. So then we had the opportunity to go on a flight test, and so what we did was we first did some high-speed taxiing to just make sure that this wouldn't fall off mid-flight, and then we just did 5 touch and goes. We found that the housing stayed secure and that we had the sensor data like recorded, and I'll show you the graphs. Now, you can see here on one of the landings, the LiDAR was very accurate, but the sonar was picking up max at a full for a lot of that landing up until the very end. You can see the same happen for the second landing with the LiDAR being even more smooth. And in this one, we never actually landed. We just kept going at a very low altitude and then took back off again. And you can see here that the sonar is just reading a whole bunch of noise, a whole bunch of garbage. And because of this stuff, because of this data, we decided that the sonar was not going to be reliable for our testing, our purposes. And the reason we believe is because wind speed, the inherent sound of an aircraft environment, the sonar is just not going to be able to pick up and parse out that kind of data. So in conclusion, the LiDAR worked extremely well. It met all of our requirements for this, and the sonar was just not suitable. We believe that there's another sensor out there that could be capable of being added to this project that would add that redundancy that is required for this project. And now Daniel's going to talk about future work opportunities.
So now for future work, what can be done next on this project? So first off, in regards to the housing, so we'd like to test the final design in accordance to how we spelled it out in our acceptance test procedures, which in particular is we'd like to do a wind tunnel test. So we'd actually like to figure out how much drag this creates and see if we can minimize that. In addition, we'd like to create a sleeker and more durable version 2. This was more of a proof of concept with glued together and bolted together. But in particular, we'd like the sides to be curved. And that way, sideward wind flow wouldn't factor into this as much, because right now they're just purely flat. We'd also like a smaller form factor. This is a little larger than it needs to be. I mean, you can see the hardware sticks up about 1.5 inches or so above what it really could. So that would be the next steps to take in housing. Now for the arm, one of the big things is we'd like the application to actually run in the background. As it is right now, the pilot actually has to pull the application up and then turn on data logging. And so they can't run it in the background with music or pull up a map or whatever. In addition, we'd also like to perform some UI tests with multiple pilots and get some feedback on what they think could be improved or what they liked and what they didn't. So now for the next steps for our ASM, we'd like to analyze and review sensor data processing, and in particular, we'd like to figure out a way to have this device detect when we're actually in a landing mode, aka during our flight test, there were occasional times where we were 600, 700 feet up, and occasionally we'd just get a noise reading of 30 feet. And obviously that wasn't accurate. And so we'd have to do some data processing to realize that that 30 feet was an outlier due to noise, and that the value should be ignored. In addition, we'd also like to do data capture for creating a landing profile. We'd like to do that a little more better than we have right now. We log the data, but it would be a little easier to implement it in a better way. In addition, we'd also like to add another sensor. In particular, a radar sensor would be wonderful. Radars are often very expensive, but it's certainly something that can be done. The radar that we tested, we weren't ever able to get raw data out of it, and we also didn't get help from the people who made it, so we had to scrap it early in the project because we just didn't have time to implement it. So then the next steps with testing is we'd like to perform all of the tests that we described in the acceptance test procedure. So we'd like to do more ASM ground tests where we didn't have corrupted data due to power cycling. In addition, as I've already mentioned, we'd like to do a wind tunnel test. Finally, we'd like to do a multiple arm test where we have multiple different tablets, say one for a pilot and one for an instructor, and make sure that they both are hearing the same data at the same time and that there isn't any confusion between the two. And then finally, FAA certification if possible. So with that, we're going to get into the conclusion. So first off, we made a list of this would be the cost of this product if we were to mass produce it as is. And one thing I want to note is we actually have added the radar module. It's this one right here, and it's quite an expensive module. We are hoping that this module could eventually work and we could actually get raw data out of it, so we've included it in our cost of mass production for that purpose. But obviously, if we take it out, this number drops from about $680 to like $400 or so. And with that being said, the product that we've delivered is that we have a housing concept adequate for testing. So this housing, we've tested it, it works on an aircraft, and we can do further testing with what you have right there. In addition, we have a PCB and hardware that enables all the functionality we need for the ASM to properly function. We have an arm that is able to alert the pilot of necessary flight information, as well as if a sensor fails or the two devices get disconnected. And in addition, one great thing about this project is even though we're all CEs, with the exception of Grant being an SE, it was actually a multidiscipline project. So we had to do software, we had to do hardware, and we even had to do mechanical design, which was kind of new to all of us. But it allowed us to dip our hands into something we never tried. And then as well, we released all of our documentation describing how we did this project and all the parts we used throughout it. So with that, are there any questions? If you think of any after this PowerPoint, please contact me at my email or our advisor, Professor Kodimer. Thank you.
Can I ask you to go back to the slide showing the landing path?
Landing, you mean one of the test routes?
Yeah, for the aircraft.
Sure.
When you had those. So what are the units on the vertical scale?
So the units are centimeters, so just kind of divide that by 100 and that'll give you meters.
So it's starting at 30 meters?
Yep.
Yes, correct. Okay, which is about 100 feet. So, oh, and by the way, the tablet, I'm not sure if you can see it, but I'll show it around. It actually shows the altitude in both centimeters and in feet. So it's applicable to both European and American pilots.
Follow, since you have that graph up.
Sure.
Why such horrific results on the sonar that previously worked and all of a sudden does not work at all?
So one thing I noted was I was actually in the aircraft when we were testing it, and when we were simply on the ground beginning to take off, when the throttle was fully increased and we had all the air flowing back, the sonar would suddenly spike to max. And so as soon as I saw that, I knew that's the problem, because the sonar pulses through air. And so when you have so much airflow, and remember this is a low power device, so when you have so much airflow, it just distorts the signal and it never gets its read back, so it defaults to max.
I will say, as a follow-up to your question, unfortunately, this was actually the first time we ever did it in an environment such as actually attaching it to an aircraft. All the other ones we were just stationary on the ground, simply looking at the sensor readouts. But this one we actually were in an environment to where it could potentially disrupt the signal from the sensor, which it did.
Every single one of these tests I'm seeing is horrific failure. I mean, I'm gonna go down a limb and guess you have Doppler effects taking place, which push you outside of the bandwidth of the receiver on the ultrasound sensors. It's something fundamentally catastrophic. It wasn't meant to be functioning at such rates, if you will, at such speeds.
Yep. Yeah, I'll agree with that. And I mean, like this one, you see, it never responds to what we've already landed. Yeah.
So I believe that your idle power consumption was actually slightly more than half of your operational consumption.
I believe that is true,
And
but I can go back.
I was wondering if you were thinking about in a future version to have something that would turn itself on as the pilot got closer to ground, as opposed to having to tell it you're gonna land.
Yeah, and that's what we kind of talked about in the future work with the landing detection algorithm, determining just without them actually having to do any physical UI work to say, all right, these guys are actually coming in to land, let's turn it on, let's actually power this up, and then we'll.
Maybe a more intermittent ranging, and as they get closer, you increase the frequency of ranging until you begin to report.
Right, and that's what it does currently, where it detects, okay, where, you know, it pulls at a slow rate while in idle, and then once it detects that the LiDAR is no longer at its max value, then it turns on high pulling. The problem with that
So
is
it does that already.
the problem with that is it has noise in it. So when we're in midair, we suddenly get a reading of 30, now it thinks it needs to turn it on, then it turns it off.
So filtering it properly, you might still be able to do this where you wouldn't have to go, I'm about to land, but just let it tell you that you're close to land.
Correct. But as it is, we'd have the instructor push the button. In my case, I pushed the button on the pilot. Yeah.
What would your plan be for some type of an algorithm? Would you be potentially integrating, say, GPS data to see are we below, say, 300 feet above ground level, or what would your plans be for a future integration like that?
So we did actually talk about GPS a little bit. It was not part of the design and plan that we had here, but one of the actual big talks about the GPS was that we were interested in not just showing the altitude as a pilot was landing, but also their position as they were landing, because they could be decreasing their altitude at a regular weight, but miss the runway. So in terms of could we verify, so I believe your question was, can we verify between a GPS, what it expects us to be at, versus what the LiDAR and sonar and any other instrument we put on there?
Or just what your plan was for detecting, at what point you start giving the enunciations for
Okay.
a landing detection algorithm.
So that would require some like filtering out algorithms, like a Kalman filter or something like that. We haven't done extensive research into that just because we've tried to get everything working in time, but it's definitely something we want to do in the future.
So kind of in that vein, what was your sample rate?
So we're sampling the sensors 10 times a second.
And how often do you record?
10 times a second.
Well,
We're also doing averaging of the data, so we fill up a buffer of 5 sensor samples, and then we average that buffer, and that's what we report to the pilot. And that's kind of our filtering right now.
Do we know of any reason why Bluetooth or Bluetooth Low Energy couldn't be used?
No, we did not extensively test it because we were pretty set on Wi-Fi having higher power. We didn't want to get halfway through and realize Bluetooth wouldn't work.
One thing I want to say about the Bluetooth versus Wi-Fi is if you use Wi-Fi, the programming model is dramatically reduced because TCP programming in Unix is very simple, but Bluetooth programming is a lot harder in an embedded language like C++.
Any other issues with Bluetooth that might impact your requirements or your ability to meet your requirements?
One thing, so we have a requirement of having multiple altitude reporting modules connect to our sensor module, and with Wi-Fi, we're able to do that because the sensor module turns itself into a hotspot and acts just like a Wi-Fi router. We got multiple devices connected to that very easily.
How did you address the problem of a flight line having 10 of these all at once operating?
Sure. So that's a really good question. So when the sensor module acts as a hotspot, it has a basic service set identifier. So that's basically like your Wi-Fi name at home. So if we were to go into manufacturing, we would have to assign like a unique ID to that name. And then the pilot would just have to remember, oh, I'm ASM 001 or I'm ASM 002. He would just have to remember to connect to his specific ASM when he's on the ramp.
You didn't say anything about battery in terms of replacing or charging it. Did you have?
It actually is a rechargeable. It is
But I
rechargeable.
mean, physically, if you owned one of these things and it was on your airplane, what would be the whole process of making sure your battery was always charged when you took a flight?
Well, one, like we showed with the UI, it actually does display the battery status on there. So you can read, oh, I have 60% battery life left. And so that way, it's kind of a visual recognition to say, all right, I just have this much left. But it'd be more of on the pilot to, after each flight, potentially just charge it up fully so they're prepared for next flight to make it.
So is the charge capability already on your board?
Yes. Yes. Sure.
You just have to actually take the board out of the housing in order to actually get access.
Correct.
So like a future iteration, we would like to add like some sort of door hinge or something where you can get easy access to the charging port without having to actually take the top off of the housing.
And another thing, our preliminary testing, so we estimated about 14 and a half hours. We were easily able to get over 10 hours out of it before the batteries would die from full charge. So that the point is that's plenty of life for a lot of small flights.
Given that this is designed for rescue pilots, student pilots, and that sort of audience, would they also be? I'm not a pilot. Disclaimer. Would they also be interested in your log data as some kind of a diagnostic tool for their landing skills as well?
Absolutely, and in fact, I believe I talked about that in ASM Next Steps. A future thing we'd like this to have, it already has some limited capability of this, but the ideal thing would be, a flight school would attach this to their airplane. They would record the data of, whatever student was landing, and then they'd review that data and figure out how well the student approached and landed during the last 100 feet, which is the last 5 to 10 seconds of landing.
Yeah. Right now,
Which
it's
would also argue for some kind of a module to get their location as well.
Yeah,
absolutely. Right,
So
right,
you
like
could
a
combine
GPS.
the two, and then it would be very valuable. Sorry.
Yeah, right now we don't have the most elegant solution for offloading that logged data, but I think in future iterations we want to create some sort of software tool or GUI to offload that data so it's a lot easier for the user or pilot to review that.
Right.
Have you given any thought to security, having a wireless hub that can be connected by any device that doesn't necessarily have to be a trusted device?
We have a password on the hotspot itself, so you have to actually log into the Wi-Fi to be able to be connected to the devices. So that's one level of security. But beyond that,
Yeah, as it stands, the data getting sent from the sensor module to the tablet is unencrypted. So if this were to kind of take off as a product, we would want to add encryption to that data.
Have you given any thought to like temperatures, what could be outside? Like, so if I'm a bush pilot in Alaska and it's below 0 degrees centigrade, will it still work?
We haven't been able to test that, but the sensors, according to their specifications, should work within those ranges. And that was one of the things we looked at because it's going to be up high in the aircraft, which is going to be much colder than it is here. That is one of the tests we actually went before, and we were able to test the sonar and the LiDAR, like when it was cold and there was snow. We were able to test it on that, and so it did work into those. But under like the extreme cold, like as you said, like an Alaskan bush pilot, we haven't been able to test that. That is something we would like to do in further testing.
Yeah, we only really tested it at Snowmageddon, if you guys remember that this year. And then also we tested it on hot days, but we didn't go to the extremes of the Sahara or Alaska for the cold. So
On that vein, business about the environment affecting, I know that you haven't had much time to do environmental kinds of testing, but there are little simple environmental challenges that are popping into my head with an optical sensor. That doesn't happen very often here in Arizona, but in the Northeast happens more often?
Trees.
No, not those, a little more, thinking of rain.
Yeah.
And
So we touched on it.
I was gonna say, because that's one of the things with the LiDAR is that if the optics of the sensor actually get like disturbed or like covered, then that could actually give unfavorable data, which is one of the reasons that we really wish we would have gotten the radar module working, because radar module would have been a great application for this product. And unfortunately, we didn't get that working, but with what we have now, it works in clear weather, which was really our main, make sure that we get clear weather working, and then potentially in the next upgrade, work on actual full weather resistance to make sure that no matter what weather condition, the housing itself is weather tight, and the sensors will also work optimally.
Here's your idea of data fusion, not so keen on how you use it, but aside from that, the idea is very strong, because then you have redundancy and robustness through the redundancy. Unfortunately, the other sensor doesn't look like one I want to buy.
Yeah.
Where you're at.
Yeah.
But something like a radar would be.
Yeah.
Did you find in this program any reason why the TI radar would not be a sensible third sensor?
Just because, short answer, no.
Thank you.
It's
Yeah.
demo worked.
Yeah, long answer, it just had so many features that we didn't need. Like it could count the number of people in a room. It could like theoretically see through walls and stuff like that, which we don't need that kind of stuff. And we just needed raw data, and they just weren't able to give us raw data out of it. And we tried contacting them, and it was just
It was a technical support nightmare.
yeah.
For everybody, let me contribute just a little bit. I also banged on TI's door. And unless you were ready to buy $1 billion of them, they just don't want to talk to us. But, okay, I just wanted to add though, the radar module we selected was aimed at some end user application.
Yeah.
They do sell a kit of components, and that would make an excellent next project.
Yes.
Oh, well, so along that line, I mean, the TI that you were looking for was kind of a canned application.
Correct.
From having been on the sales end of that, if you sell kit, then the support cost is gonna be substantial, and that has to be included as part of what you pay when you buy one of these things. So if you look at other radars that pay more in a do-it-yourself kind of module, approach that you would, you could use for more customized development.
I have no doubt that you could design a custom board around a radar using certain.
Well, I meant in terms of the options that were available to you, such that you would be in a position to have more support and more available to raw data, as opposed to buying just,
Just a single,
Yeah, we
Sure.
we looked into that, but a lot of the other radar modules were just so much more expensive than what TI was offering, even as a kit. And so we decided that given the money, we just didn't want to spend that much money on a module, especially considering the time constraints we had of building a new, essentially a new board off of that from the ground up.
So was that higher cost also continued into the unit, into the, quantity costs, or was that just because it was a development board situation where the high support costs?
We would like to implement it, and so we wanted to basically show, here's how much the product would cost if the radar was working, so basically give you the worst price estimate. And therefore, obviously, we got the sonar working or something like that, we didn't need the radar, obviously it drops the cost of the product significantly.
Have you tested the lifespan of the rubber suction cups due to the extensive change in temperature at takeoff and landing at high altitudes?
No, we have tested them over time though, we left them on surfaces over nights and days, but we didn't vary the temperature or, splash water on them or anything.
Did you do any other tests besides aircraft on those suction cups?
Yes. Yeah, we tested the suction cups, actually, we tested them on the bottom of a sink over a day, and we also tested them in a truck driving at high speed to see if they would wiggle or break off, and they didn't. They held their ground. So they're pretty strong suction cups.
Did you speculate as to why you were getting the power cycling issues when you got to the Dells?
What we thought was there's a faulty connection between the Pi hat and the actual Raspberry Pi. There was some sort of misconnection there, and that was just causing some power cycling. We haven't been able to actually replicate replicate it since then. So we haven't been able to do further testing on that.
I can see that maybe arising again in an inopportune time when they're flying with high crosswinds. And also with the suction cups, I tested them in sort of nominal conditions, but I don't know if I would trust them during a rough landing or high crosswinds.
Absolutely. And we wanted to test them like that. We wanted to test them in the wind tunnel and stuff. We just were unable to find time for this project to be able to find time to actually do testing on that.
So right now you have to turn on to start collecting data, right?
Correct.
But you tested that you wait until it's about 30 meters and it'll start picking up data automatically? Is that what you said?
No, you turn it on and that's when it'll actually start collecting data.
So if you wanted to do the way of, you don't have to turn it on and you just want it to automatically turn on when you're close to the ground, you said sometimes there's like an anomaly and then it thinks that it's on like really close to the ground and it'll start collecting data and wasting battery. Have you thought about maybe saying you have to be, it has to take this information of being 30 meters or lower for like 10 seconds and then it'll say, now I'll automatically start collecting data.
Well, 30 meters for 10 seconds, you've almost landed by that point.
Well, you can choose your time, but so it doesn't automatically turn on when you're really high in the air for one missed data point.
No, it does not turn on reporting. It turns on high pulse or high data collection.
I was just gonna say, so kind of like what you were saying, Danny, so we have those outliers like right in the beginning where it jumps up to 30 and then jumps back down to not being able to read anything. So kind of what you were saying, we want to do some filtering / processing kind of in these sections or right in this section, and then we can start reporting to the pilot their altitude. Because then we're pretty confident that the aircraft is actually landing by that time.
Something you, I'll just add another contribution, something you didn't state in here, but one of the impetus for the project is that an altimeter, nobody has, is useless in the last 100 feet. For those who aren't aware of it, you know, pilots should not be looking at an instrument at that time. Okay, so, and also notoriously inaccurate in the last 100 feet too. And it's not really that good. So for those reasons, that was the impetus of the project. What do you think explains all of those outliers that are occurring at high altitude at the beginning?
Good question.
Oh, I'm looking for a good answer.
I really do not know. And you'll actually see in this one, it actually seemed to do a little better, which was honestly strange about it. I believe that the LiDAR wasn't perfectly positioned. And we have 2 cutout holes for the LiDAR. And when we mounted this thing, the LiDAR was a little offset from that. And I think that's my theory as to why it wasn't quite working.
It's just a hypothesis, but is it possible that those outliers are preceding the runway surface area when you're over bushes and scrub? And once you're over the runway surface area, now we're getting a clean signal.
Yeah, absolutely.
Yeah, well, I mean, after the fence, it was right here when we crossed the fence.
So we're getting different reflectivities and across different surfaces.
Which is why having a radar would have been so wonderful to compare to.
Okay, well, how do you think you would solve that problem?
I think just more filtering of the data. We don't really have a whole lot of filtering besides that basic.
Filtering is a pretty
Well,
broad
and
word.
have a second module that also
Yeah.
doesn't rely on reflectivity, like radar.
Yeah.
Take, you put radar in it, you would have something to compare the LiDAR to. Right now, it's just LiDAR versus sonar, and sure as heck aren't trusting the sonar.
One thing we didn't consider, but might go in your notes, is while pressure altimeter is fairly unreliable in the last 100 feet, it could be another sensor in this, albeit it's in the high pressure airstream of the aircraft, blah, 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 but it's one more possibility.
I want to say the problem with that is the altimeter in aircraft is usually delayed by a few seconds. So cross-referencing that with the sensors on the sensor module would be pretty difficult.
But the thinking is that perhaps it could be characterized and contribute to the decision on what real altitude you have. The more is better. It doesn't cost you too much.
And perhaps be able to give you more information about when you want to cycle it on,
Right.
because you are landing. So maybe the altimeter just gives you that.
Yeah,
You turn
maybe
it
it's the on-off switch.
Yeah.
Yeah, you would have to know your landing altitude.
But you would have to reset it.
But you could calibrate it on the
Just
runway
like you
as
calibrate
we already
this.
do.
Yeah.
So it's perfectly valid point.
One other thing, kind of to that point, have you thought about the fact of, not in Arizona because we don't have trees, but going to the East Coast and a lot of airports being surrounded by trees, have you thought about any kind of protection as you're coming over the trees where regardless of your sensor, you're likely to hit the top of the canopy as opposed to ground level as you're coming into those airports?
It's a very valid point, and again, I'll go back to the LiDAR requires, line of sight, and it, requires light bouncing off. So yes, that is certainly a weakness of the LiDAR. And the question would be with the sonar, or sorry, not the sonar, definitely not the sonar. The radar fixed that. And that was something I really wish we could have tested, honestly.
For your project notes, which I'm sure you're furiously writing already.
Oh, yeah.
One idea just struck me, which is while we've been avoiding any significant interaction from the pilot, perhaps just slapping one switch saying now the landing begins might solve a lot of these problems. Just bam, you hit a button and now you know that you're in landing mode as opposed to squawking about trees, bushes, and birds.
Sure, that's kind of already what we have, though. We turn on reporting mode.
Right. Just a red button says, here we go.
Well, that's great.
So what did you use for voice synthesis?
So we literally just found an online tool, typed in a bunch of numbers, and downloaded the files, and that's what we used.
So they're canned and you just play a particular file for a particular...
Yeah, so it's like the
It's just
dictation or the
text-to-speech.
text-to-speech tool on your phone. We just found a tool where it allows you to type in text and then download an MP3 of it reading out that text. That's what we use.
So you're doing that in real time? You're generating 3 feet in text? Or
No,
you capture the different MPG files for the different heights?
Correct.
Right.
Yeah. Correct.
Do you have any plans for any potential fusion with all the sensors that are potentially on the aircraft that might help with air detection as well?
It was specifically stated in the requirements that this was not to interact with the aircraft at all. We didn't want to hook it up to the aircraft's power or to any of its instruments for safety purposes. So that's the question. No.
There's a lot of certification process that has to be gone through just to get FAA certification if you're going to hook up anything directly to the aircraft.
So on the same note as the text-to-speech, I was glad to see that you said you would, in future plans, be looking for pilot feedback on the helpfulness of the audio message, because I'm not a pilot, but I don't imagine that a beat that's increasing in frequency as you get closer to the ground is going to help in a high anxiety situation. For a young
We
pilot.
actually didn't display that, but yeah, I can only imagine.
So do you have any other ideas for audio feedback beyond the two that you
So right now we have the voice and the beeps, and then another option that we thought about adding, but we couldn't quite get to work, is kind of like a slide whistle kind of thing, whereas the frequency of the tone decreases as you get closer to the ground.
But again, how do you distinguish that? Like, how do you know?
Calibrate your ears.
Right. How do you
Exactly
know?
what you're taking
Oh,
up.
that's 1400 hertz. That must be 32 feet. How do you know? So that's kind of the biggest problem.
Just one thing to add, so it's a requirement state non-visual means, that means it doesn't have to be just audio. We can also do haptic feedback or something like that, with like a little strap on your arm that like taps you or something.
This question isn't as technical, but have you thought about giving the voice different options, like an Australian option or? You could do that.
I'll contribute one more thing here. I'm the customer of this also, so one of the things I did not want, and this team had the moxie to push back on me, I didn't want to hear words enunciated in the cockpit. Words belong to the control tower, okay? So it could lead to confusion. They push back. started using words. Good for them, I guess.
Well, the reason we push back on that is because a lot of the big iron, as you like to describe them, they have the radio altimeter with the synthesized voice. And a lot of the pilots here are going to train to fly those aircraft. So having that in these small aircraft may help them transition into the big aircraft.
I like the haptic idea. Put it in the seat.
As put a little shock wrist on. Well, any further questions from anyone?
I'll go to questions tonight.
All right. Well, thank you all for coming.